Okay, before we start, are there questions about anything? I'm just going to try and turn this light off. Okay, so seeing none, we'll just jump in. Okay, let me back up a couple slides just to sort of remind ourselves. So last class we started our attack tree. The attack tree has the goal to observe traffic sent over HTTPS from a man-in-the-middle position. We spent some time looking at what you could actually just see from outside the tunnel. So what the protocol actually just lets you see. And the conclusion from that is that you can actually learn quite a bit. Okay? So there's a lot that's not even within the purview of HTTPS to protect. Then we started considering, okay, can we break into the tunnel itself? So to break into the tunnel, we just mentioned that there's these keys that control the ends of the tunnel. If you can get the key, then you basically get access to the tunnel. Or you might be able to do something else where you try and steal the cryptographic information, maybe not directly through getting access to the key. Okay, and then we talked about side channel analysis. Okay, so the next story we'll go to is Heartbleed. So Heartbleed's a vulnerability that existed. I think I mentioned it was very high profile. It was in the news. You could watch CBC News, and there were like stories about Heartbleed. So it was a very like sort of infamous vulnerability when it occurred. Okay, so Heartbleed is a vulnerability that existed in some web servers. So it was on the server side. It wasn't on the client side. It was on the server side. And it would only affect certain configurations. So it would affect servers that were running what's called Apache. So this is an open source operating systems for servers. And it would affect servers that were running SSL, so they had SSL enabled, and they would be using the library OpenSSL. OpenSSL is the most common open source library. If you were running Apache anyways, you would press one button and then it would use OpenSSL, okay? And then the final thing was that OpenSSL could be configured in different ways, and it had this protocol called Heartbeat, and so that would have to be enabled, okay? So if all three of these things were true, then your server was potentially vulnerable to this vulnerability. Apache is super popular. Lots of people use it. It's free, right? And it was also like, it's very robust. It was developed by like Linux and IBM people. So it's a very robust operating system. So about half of the servers in the world were using it anyways. And most of them would have SSL or HTTPS enabled. And OpenSSL is sort of the default that you would use. Okay, so it would be unusual for you to not have this configuration. And at the time, Heartbeat was just on by default. And so unless if you had a reason to go in and specifically disable it, you probably were running it. Okay, so it's estimated that about 40 to 60% of all web servers on the internet were vulnerable to this vulnerability. Okay, so what's the Heartbeat protocol? So the Heartbeat protocol was this thing that was in OpenSSL. No one can really remember why it was there. It was added in like the very, very early days of OpenSSL. No one really used it. Most people forgot that it was there. The developers kind of forgot about it. It was some sort of debugging protocol. And so the idea for it was that you could walk up to a server and to just sort of test it and make sure it's configured correctly, you would send it a string or a bunch of data, and it would just echo the data back to you, okay? And so if this succeeded, then you know that it was on and running and it was configured correctly, okay? Now it had an additional feature, which is, let's say you sent it a big long string and you just wanted to echo back, like say the first 5 characters, then you could supply a second parameter, which is the number of characters that you wanted to echo back. okay? And so it could echo back less. And then if you got enough of the message, you would conclude that it was working correctly. Now, I don't know why you wouldn't just send a shorter message in the first place and have it echo back the shorter message. But anyways, this is the way it was. Okay, any problems with this that anyone can see? You're a security person, what's one thing that you might try? Just to see what happens, just to be fun. Okay, so instead of putting the data in, you could put something that would be confused with code, executable code, okay? So this is a very common vulnerability. Most vulnerabilities fall into one of two classes. So one class is that. It's that you are allowed to supply data. Instead of supplying data, you supply something that's executable. The system that receives it gets confused and it starts executing it, not knowing that it's supposed to be data. So this is actually not that vulnerability, but that is a great guess because that is like, 50% of vulnerabilities are of that nature. So it's not on the first part of the parameter. It's actually on the second. What could you do in the second? Okay, so the logic of this is if I'm sending something that's 7 characters, this number here should be like between 1 and 7, right? But is that actually enforced by the program, right? What would happen if, for example, you were like A, B, C, D, E, F, G, echo back the first 1,000 characters of what I just sent you, okay? And so these are called buffer overflows, overruns, underruns. There's different variations depending on exactly what you're doing. You could put a negative number there. There's different things that you might want to try. But in this case, it's going to be an overrun. But anyway, so what it's going to do is it's going to echo back the first 7 characters, 8 characters, 7, and then it's going to echo back a bunch of other stuff. What's that other stuff that's going to come back? Okay, so it's basically whatever happens to be in memory. So when you send this to the server, it takes a string and it puts it in memory. It puts it in RAM. Okay? And then when you're like echo it back, the operating system's like, okay, I know where that is. I remember where I stored it. So it jumps into memory at that location. And then it reads a byte. And then it says, okay, do I stop or do I keep going? Right? And so it would decrement this by 1, and there's still something there, and so then it would read the next byte, and it would say, okay, am I done? No, I'm not done. I'll read the next byte, and it will just keep reading until this hits 0, and then it will return. Okay? This is not a secure code, but this is like how code that when OpenSSL was first implemented, it might run. Okay? So that's precisely what happened. Okay? So it was a vulnerability. It would work. There was no checking, bounds checking on the string that was passed in. You could echo back everything that happened to be in RAM. You could request up to 64 kilobytes. Okay, that's how big that number could be in that parameter, and that's how much stuff you could get around. Okay. So then the next question is, okay, well, what's sitting in RAM? It's a web server. You can basically just get it to dump a bunch of stuff that happens to be sitting in RAM. Is there anything useful that's sitting in RAM of a web server? Say it louder.
Configurations.
Okay, so some sort of configurations. Sure. What else? Say it louder.
Credentials.
Credentials? Okay, who's? How about users? Let's say a user logs into the website. They pass their password. So the server has to, take that password. They have to hash it a bunch of times. They have to compare it to the password database. So where's that password sitting while it's doing all of that? It's sitting in RAM, right? And RAM is kind of like a stack. So like when you're done with it, you don't usually go and delete it out of RAM. You leave it there and then you say, you can overwrite it later, right? So if you need the space, then you'll overwrite it. But it's still sitting there until it's overwritten, okay? So the answer is that, yeah, basically everything that people are doing with the server is sitting there, and that includes a lot of personal information. So it could be usernames, it could be passwords, cookie values, data that was supplied that the server's processing, like that you uploaded, profiles, people's profiles, all of that type of stuff. Okay, now another concern would be, well, what about these SSL keys? Okay, so in order to do these secure tunnels, the server has to have a key. Okay, now there's two types of keys that are used, and I'm not going to go into the cryptographic details, but if let's say there's 100 people connected to the server at the same time, the server has 100 different keys, one for each connection. Okay, so everyone that's connected to the server has a different key. These are called session keys. Okay, but in order to set up that session key, the server needs to have what's called a long-term key. It's a key that it always uses. Okay, so if you say hi to the server, it's like, okay, I'm going to use my long-term key in this sort of cryptographic dance, and at the end of it, we're going to end up with a session key that's specific to you. So if I'm the server, it's specific to you. Someone else comes to me, then I'm going to use that long-term key again, but I'm eventually going to get a unique key that's unique to that user. Okay, so we have all these session keys. So you could break into the server, you could steal the session keys, but they tend to be ephemeral anyways, and as soon as the person disconnects and reconnects, you're going to choose a new key anyway. So it's not like, it's still useful data. You could use it to, like, if you were on the wire anyways, then you could use it to decrypt traffic that's going to the servers. But if you could steal that long-term key, the key that's used to set up all the session keys, then you can break every session key going forward. There's some caveats with what exactly you can do cryptographically with it, but let's just say it's really bad. Okay, it's really bad if a server loses that long-term key. Okay, so the thinking was, there was actually a bit of a debate about whether this was possible. So yes, it's sitting there in RAM, so it should be possible. Okay, but the argument against it, or why it might not be that practical to get this key, is it's one of the very, very first things that's loaded into RAM. Okay, and with Heartbleed, what you're doing is you're popping the most recent 64 kilobytes. So as soon as the server has done more than 64 kilobytes worth of stuff, then that key is deeper than the window that you can pop out of RAM using Heartbleed. Okay, so it's sort of past that 64K window, and so you won't be able to get it out. Most web servers, they haven't been turned off in a year or 6 months or something like that. Okay, they've been running forever. Okay, so that key is so deep into RAM that you're never going to pull it out. Okay, so that was the thinking. And one company, I can't remember who it was, I think it might have been Cloudflare or someone like that, but they basically came out and said, yeah, like this is impossible. Heartbleed's really bad because you can steal all this other data, but you'll never get the long-term keys out of any server. And then the hacker community took that as a challenge, right? And so then what they did is they came up with an attack that's sort of clever, which was that they would first trigger a reboot of the server. So they would go in, they would do something, they get the server to reboot, and then when it reboots, now RAM is empty, and then that key is within the first 64 kilobytes. So as soon as the server came back online, they would immediately hit it with Heartbleed, and then they were able to steal these long-term keys. So it was a very bad vulnerability. People actually, got into trouble. So this was one student who was just a teenager. And in Canada, he went to Canada Revenue Agency, read about Heartbleed, and he's like, oh, I should just try that. And so he picked the government website, and he hit it with Heartbleed, and guess what? It worked. And he downloaded, I don't know that he kept it or had any malicious intent. He was just sort of fooling around, but he got all these tax records that were sitting in RAM, or people's social insurance numbers and things like that. The problem is that the Canada Revenue Agency kept logs. And so later, it took probably a month or two, but after everyone knew about Heartbleed and they had patched, they went back to the server logs to see if anyone had actually ran that vulnerability against their servers, and his IP address or his parents' IP address popped up, and they went and he got charged criminally with hacking, and he pled guilty, and he didn't go to jail or anything like that. Like the sentence was sort of minimal because everyone agreed that he didn't really have malicious intent. But anyways, this is just a reminder. This was big news. It was a big thing. It did work on lots of actual websites. And as security people, if you're curious about things, it can get you in trouble. Okay, so going and just testing things, is something that you shouldn't do. Okay, you have to think through the consequences of what you're doing without, just doing it. I don't know why that's there. Okay, another idea to break into the tunnel would be to sort of mess with how the tunnel gets set up. So again, I don't want to go into all the cryptographic details, but if I go to Google and I want a secure tunnel with them, I can't have that secure tunnel on the first message. It's not like I have that tunnel, it's already there, and the very first message I send to Google is over the tunnel. Okay? What happens is we have to do this sort of negotiation where we go back and forth. We negotiate some parameters, and then at the end of this, it's called a handshake. At the end of the handshake protocol, then we'll have the secure tunnel, and then we can actually start sending messages. Okay? And if the adversary's in the middle, everything that's happening during this handshake protocol, you don't have the tunnel yet. So the handshake isn't happening in the tunnel. Otherwise you would need to do the handshake. Okay? So by definition, the handshake is before you have a tunnel in place. Therefore, it's vulnerable to tampering. So the adversary that's in the middle can mess with anything that's being said during the handshake. So if I go to a server and say, I want to connect over TLS 1.3, the adversary that's in the middle can change that to, I want to connect to SSL 3.0. Okay, an older version of SSL. And then the server will receive that message. The server doesn't know that it was changed because we don't have any crypto yet. And so then the server will say, well, you know what? I support SSL 3.0. And so then it will send me back a message. And then again, the adversary can flip it and it can say, the server is saying that it supports TLS 1.3, which is what you think you're connecting with. And so the server thinks it has like a user that's SSL 3.0, or it could change what the server's response is. It could change it from, I don't support TLS 1.3 yet. That's too new. I only support SSL 3.0, even though the server does support 1.3. Okay, so now the client says, I wanted to do 1.3, but the server only supports 3.0, so I'm going to do 3.0. It's the best I can get. And the server's thinking the user's coming to it wanting to do 3.0. Okay, so the server and the client, they're both happy, reluctant, but happy to do 3.0. They both think the other one, was the one who initiated that change, but really it was the adversary in the middle. Okay, so, and then after you negotiate the version, you're going to negotiate the crypto, like we're going to use this, we're going to use AES, or we're going to use RC4, we're going to use Diffie-Hellman, we're going to use RSA, whatever. So all of these things are called cipher suites, are also part of that negotiation. Some of these cipher suites are old. Okay, some of them go back to like very early days of, some of them go back to like the 90s when cryptography was, so I'll just tell you the full story. So, if you go back to like the 1970s, cryptography at that time was only done by governments. There was no technology, there was no internet companies doing it, you didn't use it on the internet barely existed. And so it was just a military thing. Okay, and there were actual laws in countries like Canada and the United States that said, cryptographic algorithms are like weapons. Okay, they're regulated. You can't export a cryptographic algorithm to another country. If you do, it's sort of like exporting a bomb or a grenade or something like that. Like it could be sold to that country, but the country has to qualify, and there's all this like red tape with it. Then Netscape said. So Netscape was an early designer of a browser, the internet browser. And so they said, okay, we want to do crypto, We have this SSL protocol 2.0, and we want to put it into our browser. And the U.S. government basically said no. The company was based in the U.S. So the U.S. government said, no, you can't put strong cryptography into the browser because anyone around the world can download it, and it's like they're downloading a weapon. Okay? And so there was this big, there was some legal back and forth and things like that. And eventually they reached the following position. They said, okay, Netscape, you can have two versions of Netscape browser. You can have one for US citizens, and it can have strong cryptography in it. And you can have an export version, which anyone in the world can download. But that one, you can use crypto, but we're going to make it really, really weak. So we make it, the keys are 40 bits. That maybe doesn't mean much to you, but it's something that this laptop could break probably in seconds, okay? So it's very, very, very weak. And so there were these two versions. Now Netscape themselves, when they actually rolled out the version of Navigator with this encryption technology, for some reason something went wrong and they ended up not even releasing the US version. So they only released the export version. So even if you were in the US, you still got the export version with these 40-bit keys. So basically the entire world had 40-bit keys. Now eventually the government changed, Bill Clinton came in and changed that law. And so then now it was legal to export cryptography. But what browsers want to do and servers want to do is they always want to be backwards compatible. You never know when you have a user that hasn't, is using some computer from 10 years ago, or similarly, you never, as a computer user, you never know when you're going to go to a website that was deployed 10 years ago, okay? So you want to have these old things sort of kicking around just in case you need them, okay? So even though everybody moved away from 40-bit keys, they were still there. And if there was some way to downgrade the user and the server to use these 40-bit keys, you could download them. And there was even an extreme version where it would just turn encryption off. But yeah, anyways. Now, eventually what we did is we basically made it impossible to reach those 40-bit keys. So even the software basically would stop you from downgrading all of that way. But anyways, there's a couple of points here. Let me just get back on track with the notes. Okay, so what about these attacks? Are they possible or are they not possible? And so the answer is that they were possible in early versions of SSL. So for example, SSL 3.0 could be downgraded. But then in 1.1, or sorry, 1.0, TLS 1.0, they put in countermeasures that would stop these downgrades. So if you're using TLS today and you have a modern implementation, the software itself will stop these downgrades from happening, and the TLS protocol itself also has built-in protection against these downgrade attacks. Okay, so it should be impossible to downgrade, with the one exception of there's some flaw in the software itself. Okay, so some vulnerabilities that are fairly recent have found those flaws. So they found ways of triggering code paths that end up with downgrades, even though they should technically not be possible. Okay. But mostly if the software is correct, the protocol itself will also stop you. How does the protocol stop you? So this is what the protocol does, again, without going into all the cryptographic details. What it does is it doesn't try to prevent a downgrade. It actually lets the downgrade go ahead. So you do the downgrade attack, and then you get your session keys established, and then the tunnel gets put there. The problem is the tunnel's just weaker because of the downgrade attack than what it should be. Then the very first message that you send over the tunnel is basically the client will say, by the way, this is everything I asked for in the handshake. And then the server will look at that and they'll say, okay, that's not what I heard, or that is what I heard. And then similarly, they'll send to the client and they'll say, this is everything that I understood you wanted during the handshake. And then the client will look at it. And all of this works because all the downgrade attacks, what they would do is they would downgrade the privacy of the channel. So they would let you read information, but they never downgraded the integrity of the channel. So messages that were modified wouldn't get unmodified. So if you want it in cryptographic terms, if you've taken 6110, authentication is coming from MAX. and confidentiality is coming from encryption. And so you could negotiate the encryption, but you couldn't negotiate the MAC. So you could always downgrade the encryption all the way to a 40-bit key, even to no encryption. But the MAC was basically hard-coded in. So you always had a MAC, and the MAC had strong keys, at least strong enough to get these messages back and forth before it could be broken. So anyways, that's sort of it. So this whole idea of downgrading now should not be a problem anymore. But anyways, it has historically been a problem with this protocol. Okay, here's another attack. This one's called Crime. And this is kind of a sophisticated attack, but I wanted to give you one kind of picture of what these attacks sort of look like on TLS. So again, I'm not going to go through all the cryptographic details. I'm just going to give you the sort of high level. And there's 4 or 5 attacks that are very close to this one. They use slightly different tricks in order to execute the attack, but this is sort of a nice blueprint or a template for the kind of attack that you can do. Okay. Now this attack is pretty narrow, so it doesn't let you just break SSL connections arbitrarily. You need a very specific setup, but in that specific setup, you can break it enough that it breaks some properties that you would expect HTTPS to hold. Okay, so this is going to be the setup. So instead of trying to break into the tunnel and decrypt everything, what we're going to do is we're going to target one thing in the tunnel. Okay, we're going to pick out something that's pretty small. Okay, so what we're going to target is we're going to target a cookie value. Now, cookies, we will talk about them later in the course, but you can think of a cookie as kind of like a password. Okay, usually when you log into a website, you send your password, it logs you in, then it sends you this cookie value, which is sort of like a random token. And every time you go back to the website, you send this random token, and it keeps you authenticated to the website. It's like a password. It needs to be kept secret. If I can steal your cookie value, then I can put it into my own traffic, and now the web server will think I'm you. Okay, so I can hijack your session by taking this cookie value. Okay, so cookie values are secrets, just like passwords. Therefore, they need to go over a secure tunnel. You shouldn't be using cookies if they don't go over a secure tunnel, and I'll tell you another story about that at some point. Okay, so here's an example cookie value. Now, what we're going to assume is the adversary is looking at the outside of the tunnel. Okay, so we saw from last class that you can still know what website the user is going to. You can know what server they're connected to. You can see the encrypted data. You don't know what they're saying, so you couldn't see the cookie value, but you could see things like the length of the packet and that type of thing. Okay, and so that will be important. The length will be important. All right. Now, the other thing we're going to assume is the adversary is a little more powerful than just being able to observe traffic. We're going to assume that somehow the adversary lured you onto a website where the adversary has some JavaScript running. Okay? Now, you can think of it as, for example, the outer website would be something where your cookie has value to the adversary. So it could be social media like Facebook, Twitter, whatever, TikTok, that kind of thing. Okay? And then what the adversary is given is what's called an iframe. So they're given this frame on the inside of the website. They can put whatever they want inside the iframe, including JavaScript, so they can run JavaScript. But they can't break out of their frame. So they can't just pull your cookie value out of the site that you're on. Okay? So they're running in this sort of contained thing. Maybe it's an ad library, and so they're supplying the ads. Okay? So when the user runs this website, their cookie keeps getting sent to this server. Every time they request something from the server, their cookie value is embedded. The adversary can see it in encrypted form, and then they also have JavaScript written. Okay. All right, so this is the basic setup. This is where the adversary is, what their powers are. And again, you're not going to find yourself often in a scenario where somebody is both seeing your traffic and they're controlling JavaScript on a website that you're running. But what SSL will tell you, or HTTPS will tell you, is that even if that's the case, your cookie value should be secure. there should be no problem with your cookie value because it's going over a secure tunnel. So let the adversary do that. Who cares? It doesn't matter. There's no way that this is dangerous. Okay, now this particular attack crime, it's an attack on TLS. TLS, remember, provides the cryptography. So HTTPS is HTTP over SSL/TLS. Okay, so the TLS is doing the crypto, and then HTTP is its own protocol for just sending web traffic back and forth. Some forms of TLS and HTTP, in particular when HTTP is run over something called UDP as opposed to TCP, we talked about that earlier, doesn't really matter. There's all these different sort of network protocols, and different types of content you get different ways, okay? The most natural way you get things is you do it over TCP, IP, HTTP with SSL layered on top. This type of attack does not apply to that configuration, okay? But if you're doing things like you're streaming video or other things like that, then you may be going over UDP. If you're a big company like Twitter or Google, you might have experimented with an alternative encrypted channel that's not HTTPS. So Speedy is one that was used by some big websites for a while. And so some of these things may be vulnerable to it. What it takes to be vulnerable is someone had a clever idea. They said, you know, we're sending all this traffic back and forth. What if we compress it, right? If we compress it, you know, the client compresses it, you send it, then the server uncompresses it, then the server compresses it and sends it back. That saves a lot of bandwidth. Maybe, it depends. It depends on what you're sending. But for a lot of stuff that you send back and forth, that could potentially save a lot of bandwidth, okay? Now, nothing comes for free, right? There's usually a trade-off for everything. So the server would have to spend time actually compressing the data, and the user would have to spend time uncompressing the data, okay? So there would be a delay to compress the data and uncompress it, but the bandwidth of the packets that are going back, going across would be smaller, okay? So in an environment where you want to reduce traffic and increase the computational time of your server and clients, compression makes sense. If you're using constrained devices or battery-powered devices and you care a lot about not wasting computation and you have lots of bandwidth, then you might not want to do compression, okay? So compression's not good or bad, it just depends on what you're doing, and who the servers are and who the clients are and things like that, okay? But anyway, there are a bunch of protocols that experimented with compression. Okay, so is there an attack here that we could do? Okay, so the adversary, by virtue of being able to run JavaScript, one thing you can do with JavaScript is you can open a connection to any website you want. Okay, so the user will go and you can tell the user, you know, go fetch this image from this website. And then the user will do it. They'll go to that website and they'll fetch that image. Now, if you send them to a website where the user's logged in, then the user's browser is going to put the cookie in what's called the header of that request, okay? So the JavaScript will spawn a request to a particular server. The browser is going to drop the cookie value in. So the server will see the cookie value, and then the server will be like, okay, I know who this user is, okay? Then it will send back the response, et cetera, et cetera. Now, the cookie is in the tunnel. It's in the inside of the envelope by definition. It's a secret value. It has to be inside, okay? But what the adversary can do is they can at least trigger the user to send an encrypted form of their cookie as many times as they want, okay? So they can get the user to open 10,000 connections to Facebook, and that cookie value will be in all of those requests. It will be encrypted, but they can at least see lots of examples of encrypted cookies. Okay. Again, that shouldn't help them in any way because HTTPS, because it's encrypting it, it doesn't matter. You can see 10,000 encrypted messages. It shouldn't let you decrypt it. Okay. That's what encryption is meant to detect. Okay. The problem is when you add compression to the mix, okay? So what the adversary can do is The actual request, like say you're requesting logo.jpg from Facebook, okay? The adversary is choosing that, so they're making your browser do that. Your browser is putting the cookie value in, and then it's sending this request, which includes the file name logo.jpg. Who was it that chose logo.jpg in this request? Who chose to actually ask for that file as opposed to any other file? Okay, so the answer is the adversary, right? They put the URL in their JavaScript that asks for that particular request. They can ask for a file that doesn't exist. They could just make up some random looking file name and ask for it. Facebook would say, oh, 404, like I don't have that file. That's fine, right? But technically they can ask for anything. So what you can think of is there's this packet that's being encrypted. There's a cookie at the start of the packet, and there's an adversary chosen string at the end of the packet. They're getting sandwiched together. So it's like secret cookie, adversary chosen string. We put those things together through the compression algorithm. Then we put those things through together through the encryption algorithm. Then we send the ciphertext across the wire, and the adversary is on the wire, so they get to see the end result of that. Okay? So they get to see the encrypted, compressed form of the cookie value, which they don't know, and the value that they're choosing and therefore do know. Okay. Can anyone think of, it's a sort of subtle attack, but if someone can think of it, it's great. Can anyone think of a way that might go wrong? Okay, so the remaining piece is recall that if something's encrypted, you do get to see the length of it. It might be rounded up to the nearest block size or something like that, but roughly you get to see the length of it. Okay, so the adversary is putting stuff that's getting compressed, okay? Then it's getting encrypted, and they can see the length of it. Okay, why is that useful? Okay, let's think about compression for a second. What's an example of something that compresses well? Think of a pitcher. What would a pitcher look like? A pitcher that would compress really well. What does that pitcher look like? Okay, think of it like a blue sky, and it's like all blue, right? You can say, okay, there's pixels, there's 100,000 pixels here, they're all the same shade of blue. I can tell you that in like this much space instead of sending you the pixel value all the time, okay? So any information that's redundant, any sort of patterns that exist, if there's repeated data, that's what compresses well. What does not compress well? So things that aren't repeated, there's no pattern, it's noise, it's static. If I had a random image, think of like static, and I tried to send that would not compress well. It basically wouldn't compress at all. Okay? So things that are repeated compress well. Things that aren't repeated don't compress well. Can you see whether this is going to compress well or not? Okay, you can tell that because that has to do with the length of the output. So you know the cookie value has a certain length. You're choosing the other stuff so you know how long it is, right? And so you can see whether it compressed at all, it compressed it a little, it compressed it a lot. Okay, so that's something you could see as an adversary even though you're just seeing ciphertext. Okay, all right, does anyone see the attack now? So what could I put in that purple stuff that would help me try and figure out what this cookie value is? Sorry? Okay. All right, so the idea here is I'm going to guess. I don't know what the cookie value is. I'm going to start guessing. And as I'm guessing, is it going to compress well or not? Depends on whether my guess is close. Okay? If my guess starts getting close, it's going to start compressing well. And I can see that. Okay? So what I'll do is I'll maybe guess the first, 4 bytes or the first 8 bytes. Okay? And at some point, I'm going to hit on 8 bytes that are actually in that cookie value, and all of a sudden, boom, it's going to compress those 8 bytes away because they're exactly repeated. Okay? Then I'm going to say, oh, I know part of the cookie. Then I'll guess a bit more, and eventually I'll be able to figure it out, and it's going to be a lot faster for me to do than just guessing every possible value in this cookie. Okay, I can sort of split the cookie up into chunks and I can guess those chunks. And once I get a right chunk, then I can go on and guess another chunk. Okay, so that's more or less the attack. So if I guess this value, I put it in the purple in the request, like I guess e333a.jpg or something like that. Because that is part of the cookie, it's going to compress well. And if I guess something that's not in the cookie at all, then it's not going to compress well at all. Okay, and so this is something that still takes a lot of trial and error, and everything's a little messy. Like, you know, even when you compress and encrypt, it kind of rounds numbers up and things like that. So there's, you know, it doesn't work super smoothly, but this attack actually works in real life. It does. You can pull that cookie value out, and you can pull it out way faster than you could by doing exhaustive search on the cookie itself. Okay, the limitations of this attack, this doesn't like completely break SSL because the adversary here is very powerful. They're both in the middle and they have some sort of cross-site scripting that's running, okay? And so like I say, the number of times you find yourself in a situation against an adversary that has these two pieces is probably fairly rare. They can't just arbitrarily decrypt. They don't break the whole tunnel, but what they could do is they could pull out little values like a cookie value that they could split into smaller chunks and guess it sort of chunk by chunk. It also, they still need like, I don't know what the numbers are. I'm going to say like 10,000, 100,000 queries going back and forth between the server in order to get enough data to try and figure out whether their guesses are right or wrong. Okay, what's going to happen if you generate 10,000 queries to Facebook? Well, either Facebook's going to say shut you down, right, and say that's too much traffic, or your computer's going to get hot and run and things like that, and the user's going to navigate away from the website. Or their browser's going to say this website's using a lot of resources, you know, you might want to close it or something like that. So, you know, the chances that you would sort of actually get away without some other defense mechanism kicking in is also you have a slim chance of getting away with this attack. But in theory, this is an attack and it does work. Okay, and what I want you to sort of appreciate about it is it's pretty complicated. Okay, like someone had to dream this attack up, and it involves a lot of different like little pieces, and that's how attacks are. So they're not usually simple stories. Like Heartbleed was a pretty simple story, but most attacks are more like this, where it's sort of a sophisticated thing that only works in this narrow context. Okay, so in terms of breaking into the tunnel, we can attack the protocol or the implementation of the protocol, or we can attack the cryptography directly. So if we want to attack the protocol, we can try some downgrade kind of attacks. We can downgrade the version. We can downgrade the cipher suites or the encryption algorithms that are being used. We can try and attack the server implementation to get the key. So if there's some memory leakage on the server, like we saw with Heartbleed, then that would be a way to get the key out. And if we can get the key out, then we can get into the tunnel. And we could use side channel analysis. So like timing attacks worked pretty well on very early versions of RSA that didn't protect against them. Then there's a bunch of cryptographic attacks. I showed you crime. So crime was something that used compression as, we call it an oracle when it leaks information about the secret data. There's other kinds of oracles that show up in crypto. Sometimes you have to pad out. If you're using a block cipher, it expects things in blocks of 128 bits or 256 bits. Your message will never be cleanly, divide 128 or 256. So you have to do something with that extra space. Okay, that's called padding. And so that's a variable. It depends on what the secret information is. And so you can exploit that in ways that are set up very much like crime, but I'm not going to go through the details of those attacks. And then there's other attacks that have to do with the fact that, anyways, whatever. When you take a crypto course, you can come back and you can look at this table, and you probably by then will know what an initialization vector is. Hopefully you'll know why being able to predict an initialization vector doesn't allow you to have the strongest level of security that you can get from encryption. You only get what's called CP. Actually, I guess you don't even get CPA security. But anyways, that leads to attacks. And then some encryption algorithms that were used that are phased out now had some biases in them, and you could exploit those. So anyways, crime wasn't like the only crypto attack on SSL. If anything, it was like one of 10 or 12 different attacks. And so those kinds of attacks, they're not happening every week or every month, but once a year, once every 2 years, another one of those kinds of attacks come along. So that's what I want to impress you with. And then the details of how these other things work don't really matter. And if you want to do a project or something like that, you could do a deeper dive into it. But I can't explain them well without teaching you a whole bunch of crypto. So we'll set them aside. Okay, any questions about any components of this attack tree? Okay, then what we'll do is we'll go to the third part of the attack tree. So the idea of the third attack is we're not looking at what's going over the tunnel. We're not breaking into the tunnel. What we're going to do is we're going to try and get the tunnel pointed at us. Okay? So if the user's like, I'm going to Google, I'm dropping this information into a secure tunnel to Google, but the tunnel is really going to the adversary instead, well, when the adversary pulls it out of the tunnel, there's no encryption anymore. There's no message integrity anymore, right? It's at the end of the tunnel. And so then the adversary can do whatever they want. Okay? So this is probably the most effective attack. And you'll see that there's a lot more different ways of doing this attack than in the other two kind of categories. But yeah, we'll get there. Okay, so here's a picture of HTTPS. So envisioned as a tunnel. So there's a user, they're dropping messages into a tunnel, and the tunnel is ending somewhere. Okay? Where does the tunnel actually end? Okay, so it ends at some server. Which server? Of all the servers on the internet, which one does it end at? Okay, so there's some sort of authentication. So that's the right word, but what does that mean specifically in this context? How do I authenticate the server? So authenticate just means I figure out that this is Google server as opposed to the adversary server. Okay, so DNS will turn a domain into an IP address. I will go to that IP address, but maybe I got the wrong IP address. Maybe the adversary was listening to my DNS request and they changed the IP address. So now I'm going to the adversary's IP address. What HTTPS guarantees, because they have server authentication, is that the adversary should not get away with that attack. Okay? I should be able to get a tunnel to facebook.com as opposed to this IP address. Okay? So even if I end up at completely wrong IP address, whatever's sitting at that IP address can't trick me into thinking that my secure tunnel is to facebook.com or to google.com. That's what we want from HTTPS. That's the guarantee that we want. Okay, any other ideas? Even things that you've heard about, you might not be able to explain it. Okay, so certificates are part of the story. Okay, so that's part of it. Okay, can anyone tell me what a certificate is or why it helps? What's in it?
It's kind of basically a signature from client and browser. We used to communicate a channel. They both share a certificate. If it's a valid certificate, then the channel has been made, then information is passed.
Okay, so there's these certificates. There's going to be some validity checks on it. If you can get the certificate thing right, you will get the tunnel right. Okay? Certificates involve signatures, so that's going to be part of it. Okay? So I guess the remaining questions are, what is being signed and who's doing the signing?
So basically, mostly the server signs the signatures. So the authority which is basically deploying something on the server, they basically configure it with the signature, and the client has to obtain the certificate to make the connection.
Okay. So let's just go through this a little slower. So the server signs something. Let's say that a server signs something, they send it to me. How do I know that the server signed it? Just shoot it out. So I heard CA, I heard other things.
So there is some certificate authorities that are responsible for generating certificates for different websites. In each certificate, it is mentioned which website the certificate belongs to, and there's a public part that the client can verify with the certificate authority or against the certificate of the certificate authority to become sure that this server is who he claims it is.
Okay, so there is a certificate. There are trusted third parties called certificate authorities. They're going to be involved in this whole certificate thing. Okay, but my question still is, if someone signs something, how do I know that they signed it? Like you send me an email and it's signed, how do I know that you signed it?
We have some public key integrated in our motherboard or somewhere. Those are the high-level certificate authorities public.
Okay, let me, I'm going to stop you. You're going beyond what I want to hear the word key. Okay. So we have these keys. Okay. So when you sign something, you use a key to sign it. And when I verify that you signed it, I use what's called your public key. Okay. So if I want to get into the business of signing things, I generate two keys. I have my secret key, and then I have my public key. I tell everyone what my public key is. If you get a message from me, in order to do the actual signature process, I had to use my secret key. That's why I can do it and you can't do it. You don't know my secret key. As soon as you know my secret key, you can do it too. Okay? And then for you to verify that it came from me, you would need my public key, and then there's an algorithm that you plug in the message, the signature, and the public key, and it says, yes, that's valid, or no, it's not valid. Okay? So anyway, so we can simplify the question here, which is, where does a tunnel end? We can say, well, it ends at a key. Okay? So when you set up a tunnel, what you're doing at a cryptographic level is basically you're setting it up to a public key. You're saying, I have a tunnel to the owner of this public key. Okay? Still doesn't completely answer the question because I don't know, is that Google's public key or Facebook's public key or the adversary's public key? But that's cryptographically what's happening. Okay? So your tunnel is to some public key. Okay. Now, so I have a tunnel. I know it goes to this public key. I want that to be Concordia's public key, but I'm not sure whether that's Concordia's. Maybe it's the adversary's public key. Okay? If you can solve the problem of how do you know Concordia's public key, then you completely solve this whole server authentication problem. Okay? It's really simple. If there was a big telephone book and it had every domain and every public key, then you could just look it up. Then you would be like, okay, that's great. Now I know it's their public key. Then basically this whole attack tree would be nothing. There's nothing to put there. Okay? Now it might surprise you because it sounds like a very, very simple problem. All you need is that directory of here's a bunch of domains and here's a bunch of public keys. That's all you need to solve this problem. But we're going to have a huge attack tree because it's a really hard problem to solve. Okay? Okay, so the first thing that we will try and do is we're going to use certificates. Okay, so this was mentioned. So what is a certificate and sort of what's inside of it? So a certificate is actually that directory. It's like an entry in that telephone book. It just has, here's a domain, concordia.ca, and here's a public key. Okay, it just has both of them together. So when I hand you a certificate, I say, okay, you're looking for concordia.ca's, their public key. Great, here's a certificate. Here's the domain, and here's the public key. Now, often there's more stuff in a certificate. We'll get there. But this is the essence of a certificate. This is the most important, critical part of a certificate. There might be some other stuff there as well. Okay? Now, the problem is this doesn't really solve the problem of how do I know Concordia.ca's public key, because I can get this certificate. It says what the key is. But if the adversary wants to trick me, they could also create a certificate that says Concordia.ca and has their key sitting there. Okay? So anybody can create a certificate. It's literally just, it's just data, right? It's just, here's a domain name and here's a key side by side. That's it. Okay? So anyone can send you any certificate of anything. Okay? All right, so how do we stop the adversary from, from changing the value that's inside of a certificate. So you've already said the answer, but since we're going through it a little slower, is there a way that we can stop this? Is there a way that you can protect, like say I want to send you a message and I want to make sure that nobody can change it, or if they change it, you can detect that it was changed. Okay, so hash and signature. Yeah, so hash would make it smaller and then you sign that particular value. Okay, so if we can get this certificate signed, then the adversary can't change the key. Okay, so who's going to sign this certificate for us? Okay, so Concordia could sign it, but how do I know that Concordia signed it? In order to know that Concordia signed it, I would need Concordia's key, but that's why I wanted the certificate in the first place, is because I didn't know their key. So that's circular. Okay, so a certificate authority. Okay, so what's a certificate authority, or CA?
Regulatory body that's considered a standard depending on your geographical location. So every geographical location, quote unquote, has a jurisdiction or operation.
Okay, so that's not exactly right, but it's close. So first off, it is an independent body that's going to sign it. So it's some other person that knows, that's in the business of knowing whose public keys belong to whoever's. It's not actually run by governments, it's private organizations. So there's a bunch of companies and they do this. And unfortunately, there is no jurisdiction. So any CA can do anything for any certificate in any domain, but we'll get there in a second. Okay, so an example of a CA would be a company like Global Sign. Okay, and so Global Sign will come along and say, okay, this is Concordia's public key. I'm going to sign off on it. I'm going to put my signature. So now when I show you the certificate with Global Sign's signature, the adversary can't go in and change this value. If they do, it will wreck the signature. The signature won't validate anymore. Even if you change one single bit, okay? Signatures are very sensitive, okay? So you can't change any small detail about what's being signed without wrecking the signature itself. Okay. All right, so that's good, right? Problem solved. So we have these certificate authorities. They sign off on everyone's public key. Everyone's happy, right?
How can we know that the CA is the CA?
Okay, great. So there's actually two questions, so I'll raise one, but that's one of them. So let's just go there. This information was signed by Global Sign with this signature. How do I validate this signature? I need Global Sign's public key. Okay? How do I know what Global Sign's public key is? Okay, maybe, but let me just leave it as an open question for a second. Okay? So notice it's circular again. So I wanted to get Concordia's public key, and so the solution to that was to have Global Sign sign what Concordia's public key is, but now I need to know Global Sign's public key. If I don't have Global Sign's public key, then I just went around in a circle. Okay? The second question is, Global Sign signed off that this is Concordia's public key, right? How did Global Sign figure out that that's Concordia's public key? That's what I'm trying to figure out what Concordia.ca's public key is. Somehow Global Sign figured it out. So that's fine if they're going to tell me that that's what their public key is, but how did they figure it out? And whatever method they use to figure it out, why don't I just use that method to figure it out myself? Why do I actually need Global Sign, right? If they can go around figuring out whose public keys are, they have some way of doing that, I can just do that myself. Okay? So these are the two hard problems of PKI, okay? So certificates aren't a complete answer. So the first issue is, how does Alice know the public key of the certificate authority themselves? Okay, and however they figured out Global Sign's public key, whatever, call that method A, right? They could have used that to figure out what Concordia's public key is, right? So we push the problem from what's Concordia's public key to what's Global Sign's public key. We didn't actually solve the problem, we just pushed it, okay? And then the second issue is, how did the certificate authority figure out what Concordia's public key is? And again, call it method X. They use method X. Well, that's fine. Why can't I just use method X myself? Okay? So let's go through these one by one. Okay, so the answer to this was spit out already. So how did I figure out the CA's public key? Okay, the answer is that actually I went to the Apple store, I bought a MacBook off the shelf, it was sealed in a box, I unpacked it, I turned it on for the first time, and the key of the CA was on my computer already. Okay, so the only way to make this system work is somewhere at some point you have to like embed keys into devices, because otherwise you get stuck in this circular loop of, you know, this person says it's their public key, they signed it, but how do I know their public key, and et cetera, et cetera. Okay, so and then if you get a browser like Firefox, it will come with its own set of keys. So sometimes it's the operating system, sometimes the browser has its own keys, sometimes the browser asks the operating system. That detail doesn't really matter, but anyways, Windows, Apple will have their own key stores. More or less, everyone's set of keys looks the same. Okay, you could imagine if they didn't look the same, then there could be a problem where some websites would use one that worked for Windows users but not with Apple users, right? No website wants to be in that position, so they're only going to use CAs that are on all devices, and so any other kind of CA would go out of business. Okay, so that's fine. So now the next question is, how many CAs do you think there are? So I get this computer. There's a couple. There's GlobalSign. Is there anyone? Is GlobalSign the only one? Has anyone heard of any other CA beside GlobalSign? VeriSign, maybe?
Google has its own certificate authority.
Okay.
There is Certain, there is Poplar also has their own CA. Some more.
Okay, sure. Okay, so it's not like there's one CA. We agree, right? There's like 4 or 5 CAs? Or 10? Around 10? Okay. Any other guesses? How many CAs are there? Does anyone think it's less than 10? Okay. Does anyone think it's, I don't know, 100? Oh, a few people. Okay, does anyone think it's 1,000?
Do you want us to consider private CAs as well? There's an unlimited number of CAs.
So just CAs that would be used to sign web certificates for HTTPS. Okay. How many people think it's like 1 to 10? Everyone has to answer or you get minus 10 on your final grade. Okay, 1 to 10? 10 to 100. 100 to 1,000. Okay, 1,000 to 10,000. Anything north of 10,000? Okay, all right, so the answer is it's in the hundreds, okay? And this is actually usually sort of surprising. Most people actually think it's more like 10, right? That's sort of common sense. You'd think it's probably not 1 or 2, but at the same time, it's probably not like hundreds or 200s or 500 certificate authorities, okay? But in reality, so this is on my computer. This is all the root certificates. Now, a bunch of these are like the same company has a couple certificates, and some of these are owned. Like when you really get down, you see, oh, VeriSign owns these other companies and things like that. But if you distill it down, I have the number. I think I conservatively say about 50, but it's somewhere around 50 or 100 CAs. Okay. Yeah. So this is from my operating system, actually. Yeah. So this is from the operating system itself. Yeah. So if you want to check on a Mac, you can go to keychain access. I'm not sure how to do it on Windows, but anyway, what I was showing you is the same as this itself. Okay, so anyway, there's a lot of CAs. It's maybe more than you were expecting. There's maybe about 50 unique companies, probably a bit more. The other thing is, like, most of them you probably wouldn't have heard of. Okay, some of them, yeah, there's Google, there's Cloudflare, they're kind of mixed in, but a lot of them, like Global Sign and all these companies you never heard of. They're not like businesses that you trust and are very reliable. Yeah. So who regulates them? Any guesses? Themselves. Okay.
Themselves is as in all 50 regulate one, or 5 regulate one, and that's considered a regulation for the majority is the.
Okay, so nobody regulates it. The people that kind of control it are the operating systems and the browsers, because they're putting the lists on your computer. So if Apple decides, hey, we don't like this CA for whatever reason, they could decide to not include it. Now, people might decide not to buy their computers as a result, okay? So it's sort of market forces and that kind of thing. But at the end of the day, I guess the gatekeepers are the tech companies that are putting these lists on people's computers. So basically, yeah, you can. So if you want to go and change, you can remove certificates, you can add them, you can do whatever, it's your computer.
What happens if some hacker just erase all the certificates?
Yeah, so if a hacker gets into your root store, well, first off, they could put their own root certificate, and then they can sign whatever they want, and then you have no protection anymore. And if they deleted everything, then you would get an error every single time you connected to a website. Yeah. And then back to your question. So there is an organization called the CAB Forum, so CA/browser. So basically the CA companies, the browser companies, and the operating systems too, they all kind of sit around a table and they talk about stuff. But there's no government involved, there's no laws, no one has to do anything legally. They just they try to coordinate so that sometimes it's in your best interest to coordinate with other people. But there isn't an actual regulatory body that oversees them.
So then the power lies in the product owners.
Yep. So you could say we have the power because we can.
And when I mean product owners, I mean like the actual manufacturer. Manufacturing is a step aside because Apple is manufactured in China and it's assembled in Concordia. I say Concordia, California.
Mhm.
So when I mean by product owners, I mean like the Apples, the Huawei's, the Google, so on and so forth.
Yeah, exactly. Yeah. So whoever owns a very popular operating system or a browser makes these decisions. And those decisions basically get carried over to all of their users. So all the users behind those operating systems or browsers are going along with the decision that was made by Google, Apple, Microsoft, Mozilla. That's more or less it.
So that means invariably you can never, like if you're starting from the ground up,
Yep.
you can probably never get into this 12 or 15.
Okay, so that's a great question. So why are there 200 of them? And what can you get into that club? It's a good business venture. These certificates aren't free, right? So if you go and get it, well, now there are options to get them for free, but generally speaking, traditionally, you could get a certificate, right? And how do you get added to the list? Right? And so it's a sort of who you know. And the reason that we probably have 50 companies is because in the earlier days of the internet, everyone wanted to get into this space, right? They saw it as it was lucrative. You don't have to do much. You just kind of throw a server up and you sign some stuff, right? And people pay you for that. And Microsoft didn't have a good motivation for why are we going to let this person in but not this person, right? And so, so it was very loosely regulated / unregulated / self-regulated. And then that's why this sort of blew up. So most people look at that and they say, that's too many companies. We don't need that many certificate authorities. Yeah. This sort of got out of hand and it sort of got crazy. Now, is it actually dangerous to have that many CAs? Or is it just sort of it's awkward that there's so many, but who cares? Because it's a curiosity, but there's no danger to it. Yeah, well, to the whole class. It's actually the last question here. So why does it matter that there's 50 instead of 5?
If there is, let's say there is only one CA and he become a dictator type thing. So
Yeah.
he can allow you to keep your certificate, or if he doesn't want.
Okay. So if we live in a world with one CA, you have a monopoly, and then they can charge lots of money and no one can do anything about it. Okay? So probably everyone in the world would agree that we don't want one CA. Okay? But if I gave you the choice between 10 or 100 or 1,000, which would you prefer and why? Is there any danger from a security perspective of having 1,000 CAs instead of having 10?
We're having exponentially more, I guess, CAs. It makes collusion easier.
Okay, so there could be collusion amongst CAs. So that's one possible attack. It's not the one I was thinking of. What if you hacked a CA and breached it? What could you do with that power? Just shout it out.
If that CA is one of the 50 under the 200,
Yeah.
that means that one CA can affect its trail or its own, the CA that it owns or has acquired over time.
Okay, so if I take over a CA, I can mess around with everything the CA has done. Okay, but it's even worse than that. Is there only certain things that CAs can or cannot do? So you don't necessarily know the answer. And so actually, let me just put the slide up. Any CA can sign a certificate for any website. So as long as you have a certificate from any one of those 50 companies, it doesn't even matter which one. It's all equivalent. Okay? So there's no geographic restrictions or anything like that. Okay? Now, if I'm an attacker and I want to intercept people's traffic to Facebook, my goal is to get a Facebook certificate with my key. Okay, so I want to get a CA that signs a certificate that says, actually, Facebook.com's key is this attacker's key. Okay, if I can get that certificate, I can drop it into any SSL connection and I can break the tunnel. I can have the tunnel pointed at me instead of being pointed at Facebook. Okay, so yeah.
Does that localize to Facebook, or since you said that everything is equivalent, does that mean that the Facebook attack can affect the Google attack?
So once you control a CA, you can get a certificate for Facebook and for Google and for every website you want. Okay. So now, again, why is it worse to have 100 CAs than to have 1 or 10 CAs? Well, simply you have 100 targets, right? So if you live in a world where you can compromise 1 of 10 people or you can compromise 1 out of 100, and you're going for like the worst CA, right? The CA that has the most lax security properties, right? And a lot of these CAs, they came because they're like, this is a lucrative business. Let's get into it. We just throw a server up, we sign some stuff, we make money, right? And so in the early days, people weren't thinking about the security. And so there were a lot of CAs that were like just in it to make money, and they didn't have good security measures. And you can take over one of them, it doesn't matter which one, right? Then now you can have your own Google certificate, your own Microsoft certificate, your own Facebook certificate, whatever. Okay? So that's why it's dangerous. So we don't like the fact that there's so many CAs because now there's so many targets. Yeah.
The number is just arbitrary at this point. So like if there are 10 or 100, if one can compromise 100, doesn't matter what number of CAs we have, they're already compromised with something.
Agreed. But we all agree that like more doesn't add any value. Like adding more CAs creates more security risks, but it doesn't really give you any value.
I understand that, but then like if you have a pie that's 100, that's sliced 100 ways, and you have a pie that's sliced 10 ways, and one pie, whether it be in the 100 sliced pie or the 10 sliced pie can affect the whole. The number of slices doesn't really matter at the end of the day.
So I don't really see it as pie splicing. That's a little different of analogy. It would be more like, like there's a locked door and you give 10 people keys to the door, or you give 100 people keys to the door, right? Your goal is to get into the door without a key. So you got to steal the key from someone that has the key. Would you rather be in the situation where you have 10 people that you can steal it from, or you have 100 people that you could steal it from, right? And so you'd probably rather be in the scenario where there's 100 people walking around with the keys, because the chances that one of them is careless with their key is pretty high. It's a lot higher than if there's only 10 of them.
Also, I would add that the security architecture that is put in place by the different CAs are not the same.
Right.
When we have larger numbers, so it's possible to get a weaker one than when we have a less number.
Okay, yeah, thank you. Yeah, so I wasn't making that point clearly either. So security, we sometimes call it the weakest link. It's like a chain, and every rung of the chain has to be intact, otherwise the chain doesn't hold. And you can attack the weakest link, right? So you pick the person that has the worst security and you attack them, and it's as good as attacking anyone else, right? So the system is only as secure as the worst of the worst security of the 100 people that have it. Yeah. Okay, so it's not a good situation. Now it gets slightly worse, okay? Even though our computers come with 50 root certificates or root certificates from 50 companies, most of these companies don't actually sign things directly with their root certificates, okay? Because they don't want them to get compromised, and when you sign stuff, you have to have it sitting in RAM on a server somewhere, okay? So what they might do is they might issue themselves what's called an intermediary certificate, and then they'll actually sign your certificate that you want with their intermediary certificate. And so what your computer looks for is that there's a certificate chain. So Concordia is signed by this CA. This CA has a certificate that's signed by some other CA, but eventually it gets back to one of these roots that's on your computer where there was no higher authority that signed it. It's just, we say it's self-signed, so they signed it themselves, okay? Okay, but there's no rule that says these intermediaries can't be new companies. So let's say you're GlobalSign, you have a root certificate, your friend comes along, like the US government, and says, hey, we'd like to be a CA. Mozilla and Apple, they're not letting us put a root certificate on everyone's computer, but if you sign a certificate for us saying that we're a CA, right, then we can sign whatever certificate we want for any website on the internet, and it will chain back because you signed it and you're a root, it will chain back to something that is on their computers, okay? So if you really want to know how many certificate authorities there are in the world, you can't just look at your root store, okay? You have to also look at all the intermediary certificates. The problem is, how do you find out who all these intermediary certificates are? Okay, so they're not written down anywhere. There's no record of them. They're not on everybody's operating system. In fact, the only time you know it exists is when you get a certificate that chains through them. So you get a certificate, and for the very first time you see, oh, this company has an intermediary certificate. That's when you see it, okay? So there could be intermediaries out there that you've never seen, okay? So let's say your assignment one, a little harder of an assignment, is to go count out how many intermediary certificates there are, or certificate authorities there are. How many companies have intermediary certificates? How would you count? So you can go to the 50, but they won't tell you everything that they've signed. And the root certificates will only show you the 50.
I would have to make an assumption of what the threshold is, then multiply that by 50.
Okay, so you could guess based on like what's the ratio?
I'm going to say I'll guess, like I'll back it by you said that the average is that every one of the 50 has 20 times.
Okay, but how do you even get that 1 to 20 ratio? It's a guess. Yeah.
I don't think it's feasible, but you could try to make a tool that calls to all kinds of websites in the world, get all the certificates, and then just pass that data to find what intermediaries are there.
Okay, that's actually the answer I was looking for. So the only way to get it is to literally go to every single website on the internet and see what certificate you get. Okay? Now, can you go to every website on the internet? You can on IPv4. So in IPv4, it might take you a week or two, but you can go, you do it by IP address, not by domain. So you go to 0.0.0.0, 0.00.1.2, and eventually you'll go to every IP address and you'll ask for a certificate, and some of them will be like, we don't exist. Some of them will say, I don't have a certificate, and then a bunch of them will say, we have a certificate. Now, technically, that gets you the certificates that you could see from, say, Concordia University if you run that experiment. Is it possible that a web server would look at somebody coming from Concordia and give them one certificate and look at someone coming from another country and give them a different certificate? Technically, yes, that's feasible. There's no reason why you can't do that, okay? So we don't know. Some people have tried to like measure from different places in the world, and it seems like people aren't really equivocating on the certificates, but that is technically possible. Okay, so if you scan all of IPv4, you find that there's more like 200 certificate authorities rather than 50 once you account for the fact that these 50 have given their powers to a bunch of other people. There's a newer movement called certificate transparency, where certain types of certificates have to get logged publicly. So now there's a public log of every single certificate. If you go to a website and the certificate's not in the log, then you throw away the connection. But again, it doesn't apply to every certificate, or I'm not sure the current status, but as of last time I checked, there's certain things called EV certificates that we'll talk about that mandate certificate authorities, and then others don't necessarily. But anyways, that's another way that you could try and get a sense of the number of intermediaries. Okay, so about 2 million. This number is probably actually a lot higher now. When I made the slides, about 2 million websites had HTTPS, and you have about 200 intermediaries and 50 routes.
What's the benefit of knowing the total amount of CAs?
What's the benefit of for who?
It's an open-ended question.
Okay, so there's no benefit to the user because it weakens security, right? There's a benefit to you getting into this list because you can make money giving certificates. There's no real downside to the roots doing it, probably because these people pay the roots to do it. So the roots make money, these guys make money, and so they're both happy. The users get worse security, but it wasn't their decision in the first place. And because Apple, Microsoft, Mozilla, they only control this list, they don't control this list, they can't do anything about it either, right? So yeah, so it's one of these situations where everything kind of gets worse. Some people benefit, but the people who don't benefit can't really do anything about it. It's sort of out of their power.
So what happens when a root dies?
Okay, so let's say a root certificate dies, or like say the key gets breached. The answer is that you can't do much other than update the operating systems to take it out. So we'll get to that question. Save that question for later. I'll go through all the details. There is a process we call revocation. And so we're going to study revocation. Spoiler alert, it doesn't work very well. But anyways, root certificates are particularly hard to revoke. So that will be subject to revocation. So we'll have a protocol for revoking site and intermediary, and then for roots, you just got a software update. But I'll tell you what revocation is later. I won't tell you now.
So then the subsidiaries we now to stop business will have to go through the process of re-signing to another root.
Yeah, exactly. So they would sometimes like you revoke for reasons that are benign. Like it's not because you were attacked. It's just like something went wrong, or a detail changed, or your business got bought out by another company, and now you need to put another company's name. And so you just go back to the root and get it signed again.
So is the relationship between an intermediary and a root one-to-one or one-to-many?
One to many. So one root certificate will sign.
No, I mean the other way. Can a subsidiary be signed by multiple?
Okay. So can a subsidiary have multiple roots? So we call this cross-chaining. So it means that you have multiple paths. Basically, think of it as a chain. And so you have different paths back to the root certificate. And so, yeah, it is possible. Sometimes roots will cross-certify each other. And then if one gets removed, they have a path back still. But it's sort of fallen out of favor because, first off, there's not a lot of changes that are made. And there's no real benefit because everybody has the same stores now anyways. So it is possible. It is a thing. It has been done in the past, but now there's not a real need for it because the set of CAs has been pretty stable over time. And so that's what it gives you robustness against is encountering a different set of CAs. Yeah. Yeah.
What's stopping me from creating a self-signed certificate?
Okay, so you can create a self-signed certificate, meaning that you just sign it with this public key. Okay?
Or even like one that I have created myself. Does the browser actually stop
Yeah. Okay. So what will happen is you'll go to a website, the server will say, I have this certificate. And then I'll say, okay, give me the chain from that signature back to a root that I recognize. And you'll say, I can't do it because I signed it myself. Yeah? So this happens. Now, okay, so how does the browser do it? They'll throw a warning. And it actually happened to be the case when certificates cost a lot of money that people would do it anyways. They would do a self-signed certificate. They would put their website, and yes, the user would get an error. But if they click through the error, they still have a secure tunnel. They don't have the CA signing off on it's their key. So let's say I call you on the phone and say, what's your key? And you read it out. Then your self-signed certificate is as good as a CA certificate from my perspective. Yeah. So that was there was a movement where some people would do self-signed certificates. So browser interfaces will warn you. They'll say, oh, this was self-signed. Do you want to accept it anyways? And then you can say, yeah, I'll accept it anyways. And then sometimes what they'll do is they'll remember it. So if you go back to the website and it's the same certificate, it won't show you the warning again. Yeah. So it's sort of like adding that certificate to your store yourself. So there is UI that handles those types of cases. Yeah. But it will trigger an error. Yeah. Okay, go.
Also, I think it depends on what is being used for. So in an enterprise environment where you can generate your self-signed certificate and you have that certificate being pushed to all the endpoints that is on that network, and with that it doesn't throw warning. But when it has to something connecting to the internet, like from outside accessing those applications, then it has to be publicly signed.
Okay, that's correct. So this idea of certificates isn't just for HTTPS. So a lot of other things use it. So for example, I get a piece of software, it might be signed by someone. And again, I have that problem of like, how do I know who signed it? If I'm in an enterprise environment, I might have secure messaging or secure file transfer, or I might have SSH servers, I might have VPNs. All of these things will also have their own certificate architectures. Email, I might have SMIME. And a common thing is you might have a key directory. So a key directory is just a server. Every computer is configured to ask that server, hey, what's Jeremy's public key? And then the server will say, and it will come down and it's self-signed, but because I heard it from the directory, I believe it, kind of thing. Yeah, so these are all called PKIs. So PKIs are like how these all work, kind of thing. So yeah, there are alternative PKIs, and there's ones that make a lot of sense in enterprises that don't work on the web more broadly. And yeah, there's a whole field of study, and it's interesting. But anyways, this slide is just about the PKI for HTTPS on the public internet. Yeah.
Going back towards like our question that the attacker is at the end of the tunnel. Let's say I am at the end of the tunnel. And
Yeah.
I have self-signed a certificate.
Yeah.
At that point, HTTPS will kind of take, right?
Yeah, exactly. So that's why you get the warning. So let's say I go to a website where the person running the website, I get their actual certificate and it's self-signed. So that's world A. World B, I try to go to this person's website, an adversary intercepts me, they make a certificate up on the spot. They can't get any CA to sign it because it's not the right key, but they just drop it in as a self-signed certificate. Okay? Can I distinguish world A and world B? And the answer is no, I can't. I have no way of distinguishing it. So that's why accepting a self-signed certificate is dangerous. That's why your browser will warn you, is because it can't tell the difference between it being self-signed or it being from an attacker. Yeah. So usually that's how it's worded. So we'll see. I'll actually take you to self-signed certificates. You can see how Safari today gives you that warning, and the wording kind of changes from year to year. But it basically will say, I can't figure out whether this website is who they say they are. It might be an impersonator or it might not be. What do you want to do? And then you can decide what you want to do. Yeah.
So what happens to this chain when quantum computing becomes a real thing? Because once the PKI is, I guess, compromised, also.
Yeah.
What happens to this whole chain?
Okay. So the thing that, like the links of the chain are signature algorithms. So this signature was generated by this public key. The only person that could generate this signature was the person that knows the private key that corresponds to this public key. Okay? So when you design a digital signature scheme, you want, well, at least two security properties, but two main ones. One is you shouldn't be able to look at someone's public key and figure out what their secret key is. Otherwise, that's pointless. You could just take their secret key and then you can sign things, okay? And the second thing is, if you don't know what their secret key is, you shouldn't be able to generate valid signatures. Yeah? So those are the two security properties that you want. And so a quantum computer for the kinds of digital signatures that you see in these certificates will break both of those properties of the digital signature. So basically, you can just look at the public key, spit it into your quantum computer, and it will say, here's the private key. Then you can sign whatever you want with it. So you can create your own links. You can have all the secret keys to all the root certificates, all of that kind of stuff. Yeah? And so how do we fix it? Well, the way that we fix it is we have to change our signature algorithms. So there are candidates for signature algorithms that are, we call them post-quantum or quantum secure. The problem is they're more expensive and they're a lot bigger in size. And so we don't want to change them unless if we have to, because it's going to make everything slower and it's a lot more data to store. Plus, we've only studied these post-quantum signature algorithms for 10 years as opposed to 30 years. So we're not even quite sure if they're secure. We're hoping they are, but they might not actually be, right? And so those are the reasons for inaction on changing these signatures. But what I suspect is right now, like if you talk to industry and government people, everyone is interested in upgrading signature algorithms within the next 5 years to things that are post-quantum. So yeah. So if we're saying in this class in 5 years, someone's watching this YouTube video, from 2030, then what I'm saying now might not make any sense anymore because we have all these post-quantum algorithms. Okay, let's take a break. We're kind of overdue, and we'll come back around 4:30. Yeah. Okay. Sure. So the question is, let's say I get physical access to your computer when it's on the supply chain. I work at the factory that's creating it. Somehow I get the repository keys for Apple or something like that. In all of those cases, you can break the whole system. So you can mess with the keys. You can put your own keys there. You can make yourself a CA, and then you can sign whatever you want. So keep that in mind. It's a good point, right? There might be a place in our attack tree for that kind of attack. Sorry? Just that you could try to take over, either like if you can get devices as they're being transported, you could change their root stores. If you can get the operating system to add you, or you can take over the operating system, or any CA for that matter, then you could do that. Yeah. So these are kind of like nation state adversaries, probably. And so that's totally feasible. And nation states may have an interest in trying to compromise HTTPS. So it's actually something that we should expect to see. Okay, so again, because every CA can issue a certificate for every site, and because we have so many CAs and we have weakest link, it's not great to have so many CAs. There are ways that you can sort of say, I will only use this CA. You can kind of declare that to your users. If they're able to get that information from you the first time they connect to your website, they'll remember it forever for however long they say. But anyways, these things are sort of complicated, and they're trust on first use, and they're not like the right solution to like solving this problem. But they are there. There's protocols like strict HTTPS and HTTP pinning, HKPK, those kind of protocols. Okay, and then this actually sort of goes to the question. Remember that CAs are not, some of them are just tech companies. A lot of them are, but that's not necessarily the case, especially when you start looking at these intermediaries. They're not all just like some tech company based in the United States, okay? Sometimes they're governments. They could be the US government. So the Department of Homeland Security has issued certificates in the past. I don't know if they're still there. If they're not a government, they could be aligned with the government. So there's a lot of companies that governments have a lot of control over. And some of them are located in countries where the governments have a lot of power, and they could just very quietly ask the company, you know, give me your keys, and the company wouldn't be able to say something publicly about it for fear of retribution, and there might not be strong journalism or things like that that would uncover the fact that this happened. And so you basically would never know it happened until you saw one of these certificates in the wild. And even then it might be misidentified in terms of who the parties are. Like the government might not sign it with like their actual name. So anyway, so the fact that there's so many CAs, not only just technically its weakest link, like you can choose which one you want to attack as an attacker. But if you're a government, you can also look and say, oh, this is a CA that's in my country. I'm going to go after them as opposed to another CA. So there are lots of stories about this kind of thing. So there's certificates. There's one in the UAE. This was a telecom, and it had put basically malware on some of its hardware devices. They got caught doing that. People thought that it was the government that was asking them to do it. A couple of years went by, and then someone woke up and saw one of their certificates in the certificate store, or it was an intermediary that was signed by something that was in the certificate store. And so there was this big movement to kick them out. So they tried to get Apple and Mozilla and everyone to kick them out of the CA store because they felt that they were very vulnerable to government manipulation. Okay, so let's go back to our original question. So remember we said, okay, these certificates, they look like the solution to the problem, but there's still two remaining questions. One question is, I'm trying to figure out Concordia's key. I don't know what it is. Now some CA is telling me what the key is. Well, how do I know what the CA's key is? Okay, so the answer is, well, it eventually chains back to something that your computer came with. Okay, the second thing is, how did the CA figure out what Concordia's key was? Okay, the CA, does Global Sign know Concordia, right? Or let's say you have a personal website. They don't know you, right? They don't know you any better than your users know you. So like what makes them special? Like how come they can, what do they do to figure out what your public key is, right? And why can't users just do that, whatever that method is themselves? Then you don't even need these CAs. Okay, so let's answer the second question. So why can't we just do what the CAs do, and what is it exactly that the CAs do? Okay, so here we'll distinguish between two types of certificates. So there's certificates, basically a certificate binds together a bunch of information. It's kind of like staples a bunch of together and then it signs it, okay? And there's a whole bunch of stuff in a certificate, but there's three pieces of information that are sort of critical, okay? One is the domain. Facebook.com, Google.com, whatever. This is what the user types into their browser, and this is where they're expecting to go, okay? There's the key. If you can get the right key for Google.com, then you can have a tunnel to Google.com, okay? The third thing you might care about is this Google.com. Is that like Google, the company in Mountain View, California? Or is this some other person that was able to register Google.com, okay? And so sometimes with certificate authorities, you care about like what's the business that's behind it kind of thing, okay? So the original vision of the web and certificates was that we would bind all three pieces of this information together. So I would go to concordia.ca, I would look at the certificate, it would have the key, and it would also say, by the way, this is Concordia University, it's located in Montreal, this is its address, it's not that other Concordia in Saskatchewan or the Concordia in the US, who might also own the same domain, okay? So I actually know where I'm going at a business level. Now this does require some government involvement, okay? So at a minimum, it would have to be a business that was registered with the government that had some paperwork. Then the CA would look at that paperwork, okay? And they would try and make sure that the person that's providing the paperwork actually works for that company, okay? So it could involve like phone meetings, in-person meetings, dropping documents off, mailing documents, all of that kind of stuff, okay? So that's how CAs traditionally would figure out that, okay, this is their key. It's because somebody who from this university is actually here and they're telling me it's their key, so I'm going to sign off on it, okay? Now, there's one big problem with these kinds of certificates is that process takes forever, okay? Takes 3 days, 2 weeks, a month, I don't know. You know, it depends on, you have to have all your documents sorted out and all of that type of stuff, okay? So what happens if, let's say you're a huge e-commerce website, your revenue is $1 million every day. Certificates, by the way, they don't last forever. So they have an expiration date. So when you get a certificate, it lasts a year. Next year, you have to go back and you have to renew it. But let's say this year you forget. So you wake up one morning, you have 100, people in your help forms saying, we're trying to connect to your website. We can't. We keep getting the certificate error. And you figure out what went wrong and you realize, oh, I forgot to renew the certificate. It expired yesterday. Totally forgot about it. No problem. I'll get a new one, but it's going to take 2 weeks because I have to send all these documents, okay? So 2 weeks, 14 days, $1 million a day, $14 million lost because you forgot to renew your certificate, okay? So that's not acceptable for a lot of businesses, all right? So what businesses did is they pushed CAs and they said, you got to do this faster. And so the CA said, okay, we have an idea. We probably can't check out all your business documents and all that kind of stuff any faster. But one thing we could do is we could maybe at least just check that you actually own the domain that you claim. So we'll have a certificate and it will just say, I have no idea who Concordia.ca is. Maybe it's the university, maybe it's someone else. I don't know. But whoever it is, this is actually their key. Okay, this is the key to whoever owns Concordia.ca. I don't know who they are in the real world, but that's it. If you're convinced that Concordia University's domain is Concordia.ca, then you are getting at least the right key because this key definitely belongs to the person that has control over that domain. Okay, so we call these domain validated certificates. So they only bind together the domain and the public key. Often if you look at the certificate, it will have the rest of stuff. Like it will say Concordia University, but the CA didn't sign off on that. Okay, they didn't check it. It's just sort of there. It's an assertion of who's asking for it to be signed, but it's not actually validated by the certificates. Okay, and then the answer was, okay, then the thing is, well, I go to a website, am I getting the EV or am I getting the DV, right? And so they said, okay, we'll tell the user the difference. Okay, we'll tell them if they're getting a DV or an EV, and we'll let them decide. Okay, if they really want to be sure, they're going to Google in Mountain View, California, and it's just a DV certificate, then maybe they don't interact with the website. That's fine. That's their decision. That's their prerogative. Okay, so this was the world that we lived in for a while. We kind of got rid of this world for reasons that I'll explain in a second. But before I do, would anybody know anytime you went to a website and saw either an EV or a DV or how you would know the difference? Does anyone remember anything about, your browser trying to communicate to you that you were looking at an EV certificate as opposed to a DV certificate? How do you even know that you're on an HTTPS website? Okay, so you have this lock icon, it says HTTPS, okay? So what browsers would do, this is just some details. I think I said all this stuff about EV certificates. So there's some humans that are involved at the CA checking details out. It could be like government issued business names and phone calls and things like that. It's slow. You can also fake who you are. So you could call up and say, oh, I'm Google. I work at Google, but you don't actually. So you have to figure out how you're going to figure out that people actually are working where they are. And by the way, there was a story about, there was someone who actually worked at Microsoft. So they were a legitimate Microsoft employee, but then they got fired, but they still had credentials for Microsoft. And so they went to a CA after they were fired and said, oh, I'm from Microsoft, we need a new certificate, and the CA issued them a new certificate, presumably to their own key. This was used for code signing, not for HTTPS, but it's the same principle. If it happens in that domain, it could have happened in HTTPS. Okay, so how do you tell the difference? And so the answer to that was browsers would show you stuff in green. So at the simplest case, you would see a green lock as opposed to a gray lock. If you saw a gray lock, you'd be looking at a DV certificate. And if you saw a green lock, you'd be looking at an EV certificate. Okay? The problem with that is no one knew the difference or even noticed the difference. You probably didn't notice. No one could tell me that in the room. And even if you did see it was, oh, it's green instead of gray, you might not actually know the difference. So then what they said is, okay, since we are verifying the company name, and this is like some government registered business name, what we'll do is we'll drop that domain or that name in as well. So this was like the latest sort of visual cue. So it would say Concordia University, and then it would have the lock. And sometimes they would put it in the actual name itself. There was different ways of representing it, and these cues kind of changed over time. But even with that change, people still, like if they went to twitter.com and it just was gray and said twitter.com, it doesn't really click that, oh, this might not be Twitter, the company that I think it is, right? And so anyways, people just weren't getting the difference. You would have to think a lot about like CAs and care about certificates and stuff like that. And so eventually browsers just got rid of the distinction. So now if you can go to an EV or a DV and it all looks the same. Okay, so the DV certificate is fully automated. There's no human intervention. It's meant to be something that you could complete within 5 minutes or an hour. And the CA is not going to try and figure out that you're Concordia University in Montreal. They're just going to try and figure out whether you actually control concordia.ca. Okay? If they're convinced you can control that domain, then they convince that you're able to say what your key is for your domain. Okay? Now, anyone can get a certificate for any domain. So if you own a domain, you can get a certificate for it. Okay, so if you own Google with 3 O's instead of Google, you can't get an EV certificate that says you're Google and Mountain View, but you can get a DV certificate because all it says is whoever owns this domain, they have this particular key. So if the user thinks that this is going to Google and Mountain View, right? Then the certificate will look great. There'll be a lock. They'll think nothing went wrong. You can make the website look exactly like Google's website, and everything looks the way it should be. But because this is Google with 3 O's, it's not going to the Google that you think it's going to. Okay, so DV certificates, they only bind the key to the domain. That's maybe not good enough for security, but it is what it is. Okay. All right. Now the next question is, I'm a CA. You come to me and say you're Concordia.ca, and I'm going to try and figure out whether you control the domain. How do I figure out whether you control the domain? What does that mean to control the domain? How can I test whether you have control over the domain or not? Any ideas? Okay, so I could ask you to put something in your DNS record. I could say, okay, you own that domain, great. Here's a value, stick it in your TXT record, and I'll check it. Now, let's say you stick it in the TXT record. How long before I see that? Unfortunately, with DNS, it could be like 3 days. Okay, DNS is slow to propagate. So that approach works. Nothing wrong with it other than the speed. And because I'm losing $1 million a day because I forgot to renew my certificate, I want something that's a little faster than that. But otherwise, it works. There's nothing wrong in principle with that. What if I just stick that challenge on the website? Right? I'm like, okay, concordia.ca / certificate.txt. I put a TXT file there, and there's that challenge that's sitting there. Okay? So that works. Okay? Now, let me ask you a question about it. Would the CA fetch that information over SSL or not? Over HTTPS? So if I don't have a certificate, I'm doing this because I want to get a certificate. That means I don't already have one. If I don't already have one, then I can't be serving up content over HTTPS until I have one, So that would have to go over HTTP. That means anyone in the middle could change that. Okay? So CA could go, let's say I don't control Concordia.ca. I go to the CA and say, I'm Concordia.ca. I put this text file there. It's not actually there on Concordia.ca. But when the CA goes and asks for it, I intercept it. It's not over HTTPS. And then I put in that file as a response, and then the CA thinks it's there. Okay? So those are attacks that you can think of. There's a third way that you might do it. That's actually probably the most common. Actually, okay, there's a fourth way that's now become the most common in the last 2 years, which is sort of that website, but you do it like an API. So you just have a sort of dedicated sort of socket that's open on your server, and the CA can walk up and ask for things. But anyways, traditionally, before that, there was an even more common way. Does anyone happen to know what it is? Okay, so it's the one we'll start with, which is they would send it by email. Okay, how can you figure out whether someone controls a domain based on sending emails? Well, what they would do is they would send the email to admin@yourdomain.ca, and it was just common knowledge that that's an email address that would be used for this kind of purpose. And by the way, you better not give that email address out to any of your users. If a user comes and says, what do you want your email address to be? Oh, I want admin@concordia.ca. Okay, fine. Then I could go get all of these certificates for Concordia.ca. Okay, so it was just sort of common knowledge that it wouldn't happen. Okay, so the idea is that I would go to the CA, say, I'm Concordia.ca. Here's my public key. Would you sign it? And they'll say, okay, if you're really Concordia.ca, I'm going to send a secret message to admin@concordia.ca. You go, open that email up. There'll be a link with like an embedded code in it. Click on it. And then when I see that you've clicked on it, then I'll believe that you must be Concordia.ca. Then I'll sign your certificate and I'll give it to you. Okay? So that's more or less how how DV certificate works. Okay, any issues with this? Yeah.
How can we know that the admin@domain.ca is the valid person?
Okay, so how do we know that that's actually the IT staff who's setting up the keys and not a normal user? Okay, good question. Any other flaws that you can see in this? Okay. Okay, so that one will come. That will be in the list. Okay, the first thing we could think about is who has access to that email. Okay, how do you get access to that email? There's that secret link. It's in the email. If you can click on it or get it clicked, then you get your certificate. Let's say you're the attacker. Okay, so I'm the attacker. I can say I'm Concordia. That email will get sent. The problem is only Concordia people have access to it. I don't, right? Okay, so how do I get access to it? Well, if I have some physical access to the server, I could walk into the server room and literally like pull the email off the server and then find the link and then send it back. Okay, then I get the certificate. Do most people check email by walking up to a server in Concordia with a thumb drive and pull their email off? We don't, right? How do we normally access email? If you have a Concordia email address, how do you access it?
Remotely via Outlook.
Sorry?
Via Outlook.
Okay, Outlook, and how does Outlook figure out that you own that email account? Okay, so I have a university account, so what does that mean? I have a username and... Okay, I have a username and password. That's all I'm looking for, okay? If I guess the password of admin@concordia.ca, could I get a certificate issued? I can, okay? So this whole model of using cryptographic keys and all this stuff, it can all be defeated if I can just get that one password. Can I get a password? How can I get a password? I could guess it, I could put a keystroke logger, I could try and use surveillance like video cameras. It's not impossible to get someone's password. They write it down. It's in a password manager. I breach the password manager. Okay, so that's sufficient to break the system. So I could guess or steal the password for admin@domain.ca. Is email encrypted when you send it? there's a secret and it's being passed. So when I send the email, if the CA sends the email, it has to send it across the internet. Okay? The secret is going across the internet with that email. It ends up in Concordia's mailbox. Okay? But someone that's in the middle that sees that email go by, is that in a secure tunnel or is it not?
No, depend on the protocol, POP3 or SMTP.
Okay. So someone said it could be end-to-end encrypted. It depends on the protocol, maybe PGP. Okay, so by default, email is not encrypted. There is no encryption on email. If you layer PGP on top, then you do get end-to-end encryption. Does anyone in this room use PGP? Okay, on a daily basis. So 2-3 people. Okay, so the 3 of you, you can get a certificate, won't be vulnerable to the attack. Everyone else in this room, your email that's intercepted by anyone in the middle they could just pull the secret out, relay it back to the CA, right? And remember, our attack tree is for an adversary that's in the middle. Okay, so we're assuming that they see this email go by. Okay, so email uses what's called link-to-link encryption. So from sort of server to server, it's encrypted, but then it's decrypted at that server and then re-encrypted for the next server. So it's as opposed to end-to-end encryption where it starts encrypted. Think of it as a tunnel, whereas instead of a tunnel going all the way across, you have a bunch of little tunnels, but things like leave the tunnel and then re-enter the tunnel as you go. And then it's also, we call it opportunistic or optimistic or trust on first use, which means like, how do I figure out the key of the person that I want to send it to? I just ask them for it, and then whatever they tell me, I believe. And if I can get the real server the first time, they'll tell me something, I'll believe it, I'll remember it. So if the adversary comes around later and changes it, I'll catch them changing it. But if the adversary is there the first time I ask, then they'll change the response, and then I'll end up with the adversary's key instead. Okay, so email, like basically, there is some security theater around email, but you can't rely on it.
Email works in 2 parts, right? You use SMTP for sending the email, and there's another part where you actually have to retrieve the email using something like IMAP.
Yeah.
So that is also one attack vector, right? If someone is not using POP3 or IMAP-S, then that can also be intercepted, right?
Okay, good. Yeah. So you have the mail server to mail server. So that's SMTP. And then the person who puts their username and password into the mail server, and then downloads the email back, like say using Outlook, you using Outlook and talking is going to use POP3 or IMAP. And so, yeah, that's a different protocol. If there's no encryption there, you could also nab it there as well. Or you could intercept it or do whatever. Yeah. But those tend to be encrypted anyways. And a lot of people use web forms now to access email, and then you'd be using HTTPS to the web form. But yes, that's correct. Okay. This is just a paper about email security and why it's a mess even after 30 years. 50 years, I should say. Okay, another thing is that secret value the CA sends to you by email, you could just try and guess it. If you guess it right, then you can get the right email. So usually it's going to be a large random number that's too hard to guess. So that's maybe solvable, but it's just something to keep in mind. Okay, back to the other point. If you own a domain, any domain, you have to know that admin@domain.ca, admin at your domain, is a reserved email address that you can't give it out to your users, otherwise they could get it. Okay. Now, is this the only one? Is it only admin?
Webmaster?
Okay, maybe webmaster. So there are more than that. So some CAs may send it to webmaster, some might send it to postmaster. So there are a couple that you should be aware of. What's admin mean? It's a dumb question. It means administrator. What language is the word administrator in? Another dumb question. But humor me. In English. Does everyone in the world speak English? Okay, so is everyone in every country that there's CAs and internet and HTTPS, are they going to use a word like admin? Not necessarily. I mean, maybe it's become so Americanized that everyone will use an English term. Okay, but it might be, a word that's not English for the equivalent of an administrator. okay? Or it could be Postmaster or something like that, okay? Where's the list of all these emails that you should know to reserve? Well, guess what? There is no list, okay? CAs just do whatever, if I'm a CA, I decide I'm going to send it to admin. That was my decision. If I want to send it somewhere else, I can decide that, and you'll see it if you come to me and ask for a certificate. Otherwise, you won't even know, okay? Now, again, let's go back to how many CAs are there? 250, right? 200 intermediaries, 50 routes. Where are they in the world? Are they all in the US? No. Are they all in English-speaking countries? No. Okay? And so all these CAs are free to do whatever they want in terms of what email addresses they send to. So what are the chances that there's at least just one CA out of all the CAs in the world that sends it to some weird email address that you didn't know you were supposed to keep aside for IT purposes? But somebody else knew it, and they came and they asked you for it, and you gave it to them, right? Is that possible? Could that happen with Gmail or Hotmail? I mean, you're talking about Microsoft and Google, like they got to know all of these domains, even if they're obscure, right? So this is a story of someone, well, first off, there was one CA, and they would send it to SSL certificates at domain, okay? But that wasn't well known. Nobody knew that that was the case until you went to the CA. You didn't really know it. And so guess what someone did? They went to Hotmail or Microsoft Live, Microsoft's like webmail, and they said, what do you want your email address to be? And they said, oh, I'll take SSL certificates. And they said, sure, go ahead. And so then they were able to register SSL certificates at live.com. And then they went to the CA and they got a certificate for all of Microsoft. Code signing, software updates, everything under, not just like webmail, like it's a live.com certificate, because that's where the email address was, okay? And that was bad on the CA because they used a weird email address that no one knew about, okay? Now, luckily, the person that did this was a security researcher, right? So they did it to prove a point, and then they published it, and they didn't actually use, I think they set it up so that the certificate that they got signed was already expired or something like that, but anyways. Oh, and then eventually it was distrusted by all major platforms. So they got kicked out of the root store as a result of that. If you really want to see a list, people have put together lists. So you can go on GitHub and people will be like, okay, here's a list of everything that we know about or that we've seen in the past. And so here's a list of what I was looking for is the number. I can't remember, I don't know, but it looks about like 20 different things that you should set aside. And then other people were mad about it and said, oh no, there's a whole bunch more that you shouldn't think about. So we have a better list, and we have 1,250 email addresses that you should keep set aside because one of them could be potentially used to register, to prove ownership over a domain and get a certificate for. Okay, so that's like kind of crazy, but again, we don't have regulators, there's no governments in control, there's no rules, CAs make it up as they go along, and this is what you get. You get 500 CAs, you get 1,250 email addresses, and it's all a mess. Okay, how does the email end up at admin@concordia.ca? I guess the answer is on the screen, so you can read it, but you can also think about it. Okay, can you literally route an email? Can I take an email, drop it on the wire, and say send that to admin@concordia.ca, and the routers will know how to send it? So just like internet packets don't work on domains, they work on IP addresses. Okay, so if I want to send it to admin@domain.ca, I have to switch that out for admin@IP address. Then it can get routed there, and then it will show up and it will say this is a mail packet. And if that server happens to be a mail server, then it would know how to parse it. Otherwise, it will throw an error and send it back to me. Okay, where do I get the IP address for the mail server? So I get it from DNS. Okay, same as the IP address. Let's say Concordia.ca accepts email, but they also have a website. Is their IP address for their website and their IP address for their mail server the same? Okay, not necessarily. Okay, so they could be the same, they could be different. If they are different, what does that mean for DNS? Well, that means there's different records in the DNS. So there's one that's like send www traffic here, send mail traffic here, send this kind of traffic here. So DNS records can have different IP addresses that are used for different things. Okay, mail server is under MX, so that would be the record that would be in the IP that's for the mail server. Let's say you were able to change the MX record for Concordia.ca to your IP address that you control as an adversary. What would happen to that email that the CA sent? They send it to admin@concordia.ca. Where does it go? So the CA looks up the DNS record. They get the adversary's IP address instead. They send the email straight to the adversary. Is there encryption or end-to-end? Can the adversary decrypt that email? Yeah, there's no actual encryption. Okay? Or it's link-to-link encryption, so it just encrypts it for that server, which is your server anyway, so you have the key for it. Okay? So if you can take over a domain record, then you can get email to that domain. If you can get email to that domain, then you can get a certificate for that domain. So once you own a domain, you can get a certificate for it. Okay? How do you take over a domain? Let's say I want to attack your domain. How do I do it? What do I actually attack? So I attack the DNS record. Okay, you get a new mail server at a new IP address. You want to change your DNS record. How do you do it? How are you able, like, who do you tell that to? Like, how do you actually change a record? And how do they know it's from you and not from an adversary that's trying to change it?
Your provider, the hosting provider, that could be anybody, like Hostager.
Okay, so it's going to be some third party that has something to do with hosting your website, but it's not exactly hosting it. How did you get your domain in the first place? I own pulpspy.com. How do I get that? How do I get that domain? Okay, I buy it. Okay, so I pay for it, but who do I buy it from? Okay, so there's some companies like GoDaddy or whatever, domain registrars, and they're going to sell me that domain, and then they're going to like give me access to the domain record. That's what it really means to own a domain. Why do I own it? Well, I can change the record for it. Okay, so how do I change the record? So when I buy the domain, I set the record up. Later I come back, I want to make some changes to it. I go back to GoDaddy. Okay, so whoever you bought your domain from in the first place, they're your registrar. Different people will have different registrars, and that's how you control your DNS record. Okay, if you want to make changes to it, you log in, and you could transfer the domain from one registrar to another. It's kind of involved, but it's technically possible. Okay, so every domain has a registrar, and that registrar is the gatekeeper to whether you can control that domain or not. Okay, now let's say I want to go to GoDaddy and say I'm you. I want to change your MX record. What stops me? Why can't I just go to GoDaddy and change your domain record? So username, password, account, that kind of thing. Okay, so again, this is another case where this whole CA model, we have certificates and cryptographic keys and all of this stuff, but if I can just get your password for GoDaddy, or I can get your password for your email client, right? Then I can get a certificate for your domain, and all this crypto and certificates and signing and all that stuff just goes out the window, okay? Just comes down to like username and passwords at the end of the day. Okay, other things you could do, they're basically kind of the same. You could just put the code, like serve it back from the website either as a file or over an API. It's fetched over HTTP. We mentioned why, because you're trying to get a certificate, so you don't already have a certificate. If you don't already have a certificate, then you have to do HTTP because you don't have a certificate. And the threats are very similar. If I can, when the CA goes to this address, this URL, if I can change the DNS record to point at my IP address, then they'll go to me instead. If I can intercept it in the middle, then I can pull the secret out, or I can replace what the website is sending back. So anyway, so I can basically do the same set of attacks. It's not that much different. And then the final thing you could do is you could just drop your key into your DNS record. Then when the domain, or when the CA goes and they fetch your DNS record, they just pull the key out of the DNS record. So it's just in a TXT field or something like that. You can put free text into DNS records, okay? Then it checks it, and then it's satisfied, and then it signs off on it, okay? This is similar. So DNS, generally, there's no encryption or authentication on it. So when the CA asks the domain, their local resolver, and they get back a key, there's no telling that the adversary didn't drop that in the middle, or maybe the adversary was in the DNS server system somewhere else. Okay, so somehow that record got propagated to the CA even though it's not the legitimate record. So there's a bunch of attacks on DNS that we won't go into. You could do a whole attack tree on them. Okay, or I can attack the password of the DNS. I can put my key in your record, then I can get a certificate for it. Okay, so again, it all kind of boils down to DNS. This one's a little cleaner because here it's like you can attack DNS or email. Either is sufficient. Here you can attack DNS or HTTP. Here you have to attack DNS. You don't have a second option. So it's technically maybe slightly more secure, but anyways. Okay, then the last question I just want to answer very quickly is why can't the user just do what the CA did? Okay, so it's maybe a silly question when you think about email. Like you could literally send a challenge to admin@concordia.ca. They answer the challenge, and then you're like, okay, now I believe that your key is what it is. Now I'll connect to you. Okay, you could do that, but it would take, even if it was fully automated, so your client sent the email and Concordia responded right away, doing that whole loop of communication would take a couple seconds, and you don't want to do that for every domain that you visit. Okay, so in theory, you could do what the CA is not special. They don't have any extra powers. The only thing is that this process is it's fast compared to like mailing documents around, but it's not fast enough to do in real time. Okay, so the CA does it once, and then they sign off on it, and now 1 million users don't have to do it themselves. Okay, but if you look at the very last one, which was stick your key in DNS, you do have to go and get the DNS record anyways as a user, okay? So if the key's just sitting there and you're able to grab it out of DNS, right, then you are doing what the CA is doing anyways, okay? The CA is grabbing things out of DNS, you're grabbing things out of DNS, you're just as authoritative as the CA, okay? So people have this idea, they're like, let's just put the keys in DNS, the users will just fetch the key out of DNS, and then they'll immediately do a handshake with that key. No certificates, no certificate authorities, none of that kind of stuff, okay? And it almost works. The reason it doesn't quite work is because between me and my DNS, I don't have a secure tunnel, okay? So I can't believe what DNS is telling me back, okay? Now, when a CA asks DNS, they know that and they take special precautions. They might ask 10 different DNS servers. They might do lots of different things, okay? But when the user does it, who knows? They're connected to Wi-Fi. Concordia tells me what DNS server to use it. I just use it. If I connect to malicious Wi-Fi, I have malicious DNS, I'm getting malicious keys, okay? So that's why we don't do it. If we had secure tunnels to DNS, if every DNS record was signed by the DNS authorities, you need another certificate authorities for DNS, which do exist, then you could actually just do this, okay? So there is a proposal to do it. It's called DANE. There is a protocol for signed DNS called DNSSEC. And the main thing that's holding it back is just it's kind of slow and big. And the records that you get are big. And we talked about how you can use them to amplify DOS attacks and things like that, okay? So DNSSEC hasn't been widely adopted. Most of us aren't using it, even though we're connected to a DNS server. And so that's why we don't distribute keys through DNS. But if we could somehow fix this DNSSEC thing, then we could just put keys in DNS records, and then we can get rid of CAs completely. Okay, any questions about any of that? Okay, great. So I will see you all next week. And don't worry, there's more to fill in the attack tree.